to take the logarithm of a negative number of 0, at least in this class. However, if any of you are math majors or engineering majors, later in your mathematics education, you will get into complex analysis or functions of complex variables. And don't be scared about the name of the subject. Complex doesn't necessarily mean complicated. The reason why it's called complex, it's because that deals with the field of complex numbers. You know, remember those equations that do not have real solutions, that have solutions that are imaginary numbers or even complex numbers. Well, technically imaginary numbers are complex numbers where the real part is 0 anyway. And well, there's a bunch of pretty cool stuff that you do in complex analysis. In fact, there is a saying there from by a mathematician that says that the shortest way between two truths in real analysis, and that is in the world that we're looking at, goes through complex analysis. And once you get to that subject, you will learn a lot of methods to solve problems in a shorter way, in an easier way than what you know using using this type of method we learn in real algebra, real calculus, etc., or real analysis actually. So it's a pretty cool subject that you will take, especially I'm talking about, well, math majors, of course, who and mostly electrical engineering, because the complex part, I mean, the real part of a number and the imaginary number have different meanings, different interpretations when it comes to talking about electrical circuits and a lot of pretty cool stuff. But well, that's going to be later. And well, so the way we denote logarithmic functions, there's one particular logarithmic function that we describe, and it's one of the most common symbols that you will ever see. That's the ln. Okay, ln. So instead of using the word or the symbol log to denote log or logarithm, we use ln to describe a natural log. It's a special logarithm, and well, the symbol ln, that's because it comes from its Latin name, Logarithmus Naturalis, right? And well, what about that ln of x? Well, so by definition of a logarithm, it's a logarithm on some base. This particular logarithm, the natural logarithm, it's a logarithm on the base e, which is that special number we talked about last time, right? So we can have logarithms base 2, logarithms base 10, logarithm base 9, base 9, base 5, your favorite base. When we can have logarithms on a base that could be irrational numbers, so logarithm base square root of 2, logarithm base square root of 3, logarithm base pi, or, and in this case, for this particular case, logarithm base e, which has a special symbol, which is ln of x. All right. And well, I'm talking about the bases and numbers, and well, but we haven't seen what these really are. Oh, before looking at that, we have what we call the common logarithm, and it's the log function for which we don't see any subscript underneath the g. You know, like in general, you have a logarithm base b. We need to write the number that it's the base of the logarithm base 2, logarithm base 5, etc. But this particular log, when you don't see anything in the subscript, that is understood that this is the common logarithm or logarithm base 10. But we don't need to write that base 10. I'm just writing it just so you see what this really means. And just like what's it called, like the square root, when you see the square root of x, there is an invisible number here, which is the number to which we don't need to write it down, unless we talk about the cube root, the fourth root. You know, well, in this case, we need to be very explicit with the index. No number in the index is a 2. It's a square root. No number in the subscript of the log symbol, it's a logarithm base 10. But what's a logarithm again? Well, it turns out it is an exponent. Well, so Okay, so let's talk about logarithmic form expressions in logarithmic form and exponential form. So that's going to complete our definition. So they're asking us to find or to evaluate logarithm of 100. What does that mean to evaluate the logarithm of 100? Well, they're asking us what power of 10 equals 100. What would that be? 2. All right, and that's because 10 to the 2 equals 100. So in this case, we have a logarithmic form, its meaning in words or in practice, and the exponential form. Let's go back and check with the definition above. Well, so log base b of x is b to that should have been a y, by the way. Anyway. Oh, no, that's fine, that's fine. So that means b to the y equals x. In other words, what power of b equals x? Let's look at more examples on how we evaluate this. Logarithm base 3 of 81. When they're asking us to evaluate the logarithm of 81 on a base 3, they're asking us essentially what power of 3 equals 81. Any ideas? How many times do we need to multiply 3 by itself to get the number 81? 4. Okay? Okay, because, oh no, that 4 goes here. And that's because 3 to the 4 equals 81. Right? Actually, if you think about it, the square root of a number, you can think of it as a logarithm because we're looking for what power of 25 equals 5, and that power is 1/2, right? So it's a logarithm base 25 in that case, right? Maybe you thought of radicals like that, maybe not, but I think it's a pretty cool connection because ultimately we're working with powers. So a logarithm is a power. Taking the square root is taking a power, but the difference here is that power we take when we take a square root is a rational power. And well, for logarithms, actually there's no limit for what kind of powers we can have. Powers with decimals, irrational powers, integers, rational, etc. Any number. There's no restriction for those. All right. Logarithm of 16 on base 4 or log base 4 of 16. In other words, what power of 4 equals 16? 2. And that's because 4 to the second power equals 16. Okay. We have another logarithm of 16. Notice that exercise looks repeated. However, we're going to do this calculation on a different base. So now they're asking us to evaluate the logarithm of 16, but this time based 2. In other words, what power of 2 equals 16? 4. That's because 2 to the 4th power equals 16. And again, I'm going to go back to the definition. Log base b of x equals y. That's because b to the y equals x. So that's how we're going to jump back and forth between exponential form and logarithmic form. And later we are going to use this powerful tool to solve equations. But I mean, I could have just told you from the beginning, oh yes, these logarithms are useful to solve equations, but no, that's not really what they are. Logarithms are actually are exponents. The exponent we need to raise to a given base b in order to get the argument. What's the argument, by the way? Let me go back to the definition. So in this case, okay, let me write it down. Log base b of x, where b is the base, and the expression that we see inside of, well, in this case we don't have parentheses, but we will have some examples in which there will be. This quantity x it's called the argument, which is the expression or the number on which we are taking that logarithm, right? So From now on, well, or actually when we get into the operations with logarithms, that it maybe next time when we get to the properties of logarithms, you will hear me using the word argument because, well, that's the expression inside. You'll see. You'll see. So let's do more practice. So we are asked to change each exponential statement involving a logarithm. Well, by definition, number one, log base b of x equals y if and only if b to the y equals to x. Okay, so here we have an exponential form. Let's write its equivalent in logarithmic form. So in this case, well, the base is given by the base of the exponential function, which in this case, this will be log base a of 44.3, which equals 3. That means we need to raise the letter a to the 4.3 to get, or I mean to the third power to get 4.3. And likewise, e to the 3.4 equals big N. Well, using the same definition. Well, in this case, notice the base of the exponent of the exponential function. This is an exponential function of base e, or also known as the exponential, the natural exponential. And when we relate a natural exponential, we relate it with a natural logarithm. So in this case, well, first of all, I'm going to write this as an ln, as a log base e of 3.4, and that equals to n. All right, so and that's in this case ln of 3.4 equals n. Oh, wait a minute, no, it's the reverse, so that's the y, and that should be, hold on, so the base is e, and the y, the x, oh no, it's ln, oh come on, that's an h, ln of n equals 3.4. So that's the logarithmic form for this, right? And notice I went from log base e to ln because they mean the same thing. For practice, we just use the ln, not the log subscript e. Unless it's a different number, 5, 7, 3. And when it comes to base 10, recall that's one that we don't write. We don't write the base 10. So in this case, well, now let's do the reverse. So we have a logarithmic expression with other symbols, with other decimals, very similar to what we did in the previous step, in the previous example. Now we're going to write this in exponential form. So logarithm base m, well, when we read the subscript, we can start already writing m as our base of some exponent, and recall that the result of computing a logarithm, it's an exponent, that is the exponent of 4 and equals 8. That means log base m of 8 equals to 4 because m to the 4th equals 8. Right? The base raised to the power equals the argument of the logarithmic function. And yes?
For e, for the one before, isn't it log base e of n?
Of n, yes, that's what I meant, but not what I wrote. Thank you. And equals 3.4. Yeah, thank you. Letter B, ln of x equals to 4. Well, it would be great, I mean, at least for now, log base e of x equals to 4. So now we're going to write, I think the subscript gives us an idea of what the exponent is, and e to the power 4 equals to x. And this is how we go back and forth between exponentials and logarithms for the same expression, two equivalent expression. And well, you might be thinking, why do we need to, why do we need this? Well, some of you are going to be working in science, in a laboratory, for example, collecting data. And when you collect data, say for a calibration curve, you know that you use as a standard solution to determine the concentration of some pollutant, for example, in analytical chemistry, right? And well, once you collect the data, in some cases, the data you output, it's in the form of a parabola, for example, or some curve, but you may need to manipulate the data in a way that the order pairs that depict the observations that you took via data collection, taking readings from different samples, they look like the equation of a line, because linear equations are very convenient, because all we do, is they sort of follow the same slope, and we can use those linear functions to sort of predict. Have any of you taken statistics, elementary statistics? Well, if you have taken statistics, well, for those of you who haven't taken statistics, there is something called linear regression. And linear regression, it's used to, well, we collect data and we fit all the points, all the observations on the equation of a line, and we use that equation of the line to predict what's going to happen in the future, or what happened before. So, of course, with some restrictions, we have to set some restrictions about an interval of convergence in this case for this, for the use of these equations. And well, coming back to logarithms, so what we do in order to obtain those linear equations is convert these data into logarithmic versions. So when you plot them using the logarithm, you obtain the equation of a line, and that's what you will be using for calibration, what we call the calibration curves in chemistry, or there's other calibration curves, not just in chemistry, in physics and social sciences, etc. You'll see when you get to the research area in your future courses. In the meantime, well, let's talk about the domain of a logarithmic function. Well, let's see. So well, here is basically the process to find the domain, but let's explain why do we just set the argument greater than 0 and solve the inequality. So let me go to the graphing calculator, and well, what do we have? Let me clear this. And so, oops. Let me type the log function. So that's log of x. And I'm going to, okay, table set. I'm going to start my table at -5, for example, with increments of, I would like to do 0.5s. So we can see, well, and in this case, I'm going to generate values automatically. And let's see, oh, I wanted a table, not, all right. Notice what we get as y values for negative numbers, because, and again, we already talked about the fact that we cannot take the logarithm, at least for now, of a negative number, because, well, the calculator is going to output an error here. So that means we cannot take the logarithm of 0. We cannot take the logarithm of a negative number, but any number greater than 0 is fine. So, and to illustrate, to keep illustrating this, let me start my table at -0.1. I'm going to do increments of 0.1 this time, so you can see that. So notice 0, we get an error, but smaller values close to 0 from the right, such as 0.1, 0.2, well, we start getting outputs about it, right? We start getting outputs, that's where the function is defined. So that's why when finding the domain of a logarithmic functions, we only consider the set of positive values as the okay inputs for the function. Then we don't include the 0. There we cannot find logarithm of 0 regardless of the base, and no logarithm of negative number, also regardless of the base. But again, complex analysis, that's going to be a whole different story. But in the meantime, let's find domains of logarithmic functions. So what we do, set the argument greater than 0 and solve the inequality for the variable. So, and the argument is this expression inside the parentheses of the logarithmic function. So what we do in this case is set x plus 3 greater than 0, not greater than or equal. The greater than or equal thing is for radical functions of even index, such as the square root function, the 4-root function, the 6-root function, etc., etc. Only even function, even root functions. So for logarithms, only less than. So, well, this is a baby inequality, x greater than negative 3. And that's our domain. Well, from here we're going to write this using interval notation. I'm going to go to the number negative 3, but notice I have a greater than only. I don't have a greater than or equal. So for this reason, when I plot this number on a number line, I'm going to represent it by an open bubble. Had we had otherwise the greater than or equal, then I would have represented this using a full bubble instead. So that's our number line. That's negative 3. And I'm going to shade on the correct side given the sign of the inequality. And you can always go with the inequality symbol. So notice how the inequality symbol sort of works like an arrow, and it's pointing towards the right. And that means we're going to shade towards the right. Now that we know what's the OK inputs for the function, what's the region for which the function is actually defined, let me change colors. I think it's too clear. I think much better, right? So we need to represent this using interval notation. So the domain, which is in interval notation from negative 3 to positive infinity. And notice for negative 3, I use the parentheses, not the brackets, because we don't include the negative 3. It's represented by an open circle, and it's only greater than, not greater than or equal. Now, we also need to get used to finding the domain of the function using a set builder notation, that is x such that, and this one usually it's easy to write because all we do is copy and paste the result, the last result on the inequality that we solved before. So that's greater than negative 3. That's it. All right. Let's look at another example. So this time we have logarithm base. What's the base of this logarithm, by the way? Base 10. So this is a common logarithm, right? The base 10, when we don't see any subscript, it's understood to be the common logarithm or the logarithm base 10. All right, so since in this case, well, actually, the domain of the function, notice, doesn't depend at all on the base. So when all we do is just set up the argument as an inequality, and we don't even touch the base, actually. So the base, it's just there. So let me highlight the argument and set that argument 5 minus 3x greater than 0. And let's solve the inequality here. So I want to isolate the x and leave the x on the left hand side. So I'm going to subtract 5 on both sides, negative 3x greater than negative 5, and I'm going to divide both sides by negative 3, and I'm going to make a mistake on purpose to see if you can catch it. Mm-hmm. Yes. We didn't flip it, right? So we need to flip the sign of the inequality every time we multiply or divide an inequality by a negative number. So do you know the explanation behind? Or you just know that that's how it works? Well, in case you don't know what we do, well, let's talk about logical sentences here. Let's take a couple minutes to talk about it. So, for example, a logical sentence here, or a logical statement rather, 3 equals 3. This is a logical statement, right? Because 3 equals to 3. And well, to keep the integrity of this statement, whatever I do on both sides of this equation, on one side of this equation, I have to do it on the other side of the equation to keep this a logical sentence. For example, if I add 2 to both sides, I have to do it on the other side. That way, 5 equals to 5. All right. If I multiply by 2, I have to do it on the other side as well. That way, this is still a logical sentence, right? Okay, what about, how can I put it? Yes, I got it. 3 and 5. So this time we are going to compare numbers, because in this case, is this true? Okay, what symbol should we use in this case? In between the numbers. Definitely the equal sign is not correct. So which one should we do? Less than, all right? Because 3 is less than 5, all right? Well, what happens if I add 2 to both sides? Well, this is 3 plus 2, that's 5. And that's 5 plus 2, which is 7. And we still have a logical statement. Agree? Okay. What if we multiply this by 3? 3 times 5, which is 15. And 7 times 3, which is 21. Is this still a logical sentence? A logical statement? Yes. 15 is indeed less than 21. Now, what if I multiply this statement by -1? Okay, what is -1 times 15? -15. What is 21 times -1? -21. Is that still a logical statement? No, that's why we reverse this, right? I know the numbers, number-wise, look the same, but be careful because these are negative numbers, all right? So careful. So that's why we reverse the inequality symbol every time we multiply or divide by a negative number on an inequality to keep the logic of the statement that we're working on. That being said, well, let's move on to looking into graphing logarithmic functions. And well, that's how the graph of the logarithmic function looks like. This is in particular the graph of log x, that is the log base 10 of x. All right? So, let's see. And well, what do we have about, what can we say about this graph? Number one, well, it's an increasing function. So it's a function that increases for y values, but maybe not as rapidly as an exponential function, right? So it grows kind of steep for some values, and somehow it starts to flatten, okay? But still, even though it doesn't look like it, the domain is all real, not all real numbers. It goes from 0 to positive infinity, but it grows faster in the x direction than it does in the y direction, okay? And the range in this case, well, this arrow indicates that it's going to go from negative all the way down to negative infinity. And every time we see graphs, so this is important when looking and when trying to find domains of functions, but when we are given their graphs. My advice is to always break up this arrow into essentially two components. What do I mean by that? Well, so this arrow, it's going right, but at the same time it's going up. That is, we can break this up like this, and this so we can get the domain in the range of the function. All right. So this one means negative infinity. This arrow right here means the graph is going to go all the way to positive infinity. So that's why the range of this function is all real numbers. Sounds good? Well, It has no y-intercept. In fact, something I didn't show about the graph is that, yes, it's colored. The vertical axis, the y-axis, is a vertical asymptote. So I think we are going to start seeing some connections between this logarithmic function and the exponential function. Similarities and contrasts, you know. And notice how the exponential function has a domain that it's all real numbers and has a limited range, as opposed to the logarithmic function has a limited domain, but the range is all real numbers. Kind of opposed ideas, isn't it? That's because these two functions are inverses of one another. Well, while the exponential function has a y-intercept and no x-intercept, well, the logarithmic function has an x-intercept but no y-intercept. So that's reverse ideas of one another. On the other hand, what else? The exponential function had a horizontal asymptote, no vertical asymptotes, as opposed to the logarithmic function here that has a vertical asymptote but no horizontal asymptote. Again, opposite ideas, right? Reverse ideas. So again, when we put these ideas together, that's where we start concluding that these two functions, the exponential function and the logarithmic functions, are inverses of one another. All right. And well, other observations here when x is between 0 and 1. It's kind of, I don't know what's going on here. Okay. So the outputs are only negative values, and everywhere else their outputs are positive values. What else? As x approaches 0, well, and by the way, it comes from the right, not from both sides, because from the left side of the graph there's actually no graph. I mean, from the left side of the asymptote actually. And well, about approaching certain values, well, that's vocabulary that we will get more into when we get to calculus. So for now, that's just to give you the idea. Okay, so let's grab the graph functions, logarithmic functions. And well, it shouldn't be surprising that the graphs of these functions will also meet the same conditions as the translations and shiftings and all that. They're exactly the same, just the same way we translated parabolas, rationals, exponentials last week, I think. So it works the same for the logarithmic functions, all right? So let me actually draw the graph on top of it because I need to shift it. Okay. So number one, before graphing the equation, let's see. What does this -3 going to indicate as a result of shifting or translating the graph? Does that mean horizontal shift or vertical shift? Well, number one is 3 units for sure, right? However, the question is in which direction? Left, right, up, down? To the right, because it's inside parentheses. Recall that any shiftings that we have inside parentheses, inside radicals, or as exponents of exponentials, those go in the opposite direction as the sign that we have. So that means, oh, come on. That means this graph will be shifted 1, 2, 3 units to the right. Sounds good? What about, okay, let me do the graph again for the second example. And okay, What about this plus 2 in this case? What is that going to do? Which direction are we going to shift the graph? Up. How many units? 2 units, right? So in this case, I'm going to move this 1, 2 units. Well, what's the reference though for moving this, for shifting this graph 2 units up? Well, we can use as a reference the x-intercept, which is the point 1, 0, and from there shift it up 2 units. And I think this is represented 1, 2. I don't think so actually. Let me do that again. So that's 1 and 2. Yes, it's right here. Right? So it's shifted up 2 units. Well, how about we find the domain and the range of these functions? Well, number 1, the domain, which is the OK inputs. In this case, well, we can use setting the argument greater than 0 as an inequality. Or we can just look at the graph and see how we have a vertical asymptote at x equals to 3, and we have points on the graph to the right, so we can simply say domain equal, it's actually positive 3, not negative 3, 3 to infinity. And the range is simply all real numbers. Well, actually, of course, x such that x greater than 3 and y such that y belongs, in this case, to all real numbers. If we do the same for the function that gets shifted up 2 units, the domain, it's still the same as the original function. We will conclude something about it. So 0 to infinity. And range, all real numbers. And x such that x greater than 0 and y such that y belongs to the set of all real numbers. Now, let's put this, let's observe the 2 graphs and conclude about the bigger picture. So for a logarithmic function, the domain gets affected by a horizontal shift, but it doesn't get affected by a vertical shift. And that's a reason why I got 2 individual shiftings for each, so you can see the difference. So again, domain, it's not affected by a vertical shifting, by translating either up or down any number of units, but it affects its domain when we translate units in the horizontal direction. All right, so let's see what's next. Let's see if, well, how about we look at the next topic next time, so we start fresh again on coming up with ideas that we discussed today.